I want to take a look at the second derivative, and one of the things it tells us about a graph is whether a critical point is a maximum or a minimum. So here's an example where I've got y equals, let's just do a quick parabola here, so x squared minus 6x plus 8. If I want to know where's the critical point, where's the place where the tangent line is horizontal, I can look at the derivative and set that equal to 0, right? This is critical if 2x minus 6 is equal to 0, so 2x equals 6 and x equals 3. So I've got a critical point at x equals 3. Is that a maximum or minimum? Local maximum or minimum? I mean, it could be either. I just know that I got a tangent line that's horizontal there. It could look like this. It could look like, wait a minute, it could look like that. Well, you know, you and I probably already know that it's going to be this one because this is a positive coefficient in front of the x squared, and it's a parabola that opens up, so it's this one, and I got a local minimum. Okay, but suppose I didn't know that. What I can do here is I can look at the second derivative. The second derivative is equal to 2. Positive second derivative means that the graph is concave up. Concave up. It's bending upwards. If I have a spot with a horizontal tangent line and it's bending upwards, then that must have been a local minimum. Local min at x equals 3. Right? X equals 3 is my critical value, and it's bending upwards, so it's a local minimum. This is what's called the second derivative test. And let's write this down. The second derivative test. Let's spell second this way. Second, there we go. Derivative test. Second derivative test says this. First of all, if f prime of c is equal to 0, so let's say you're at a critical point, then if f double prime of c is positive, just like we had here, then we have, then x equals c gives a local min, right? If the second derivative is negative, then you're looking at, well, we already started off a place with a horizontal tangent line. So this one was this picture right here, horizontal tangent line concave up, it must have been a minimum. This one is now horizontal tangent line concave down, so it must be a local maximum. Then x equals c gives a local max. And lastly, if f double prime of c equals 0, then all bets are off. A calculus text would probably say the test is inconclusive. Right? Let me point out here why all bets are off. Note, y equals x cubed. The derivative is 3x squared. The second derivative is 6x. So at x equals 0 is the critical point, right? And it's also an inflection point. So concave down here, concave up there, you know, it's not a max or a min, okay? Furthermore, if you look at y equals x to the fourth, then y prime equals 4x cubed, and x equals 0 is a critical point, and y double prime is equal to 12x squared, and so x is an inflection point. Actually, it's kind of a double inflection point. This one looks like this. It's really flat, and it's really straight right through there, and then it goes back up again. So here we had a second derivative equal to 0 was neither max nor min. Here I got a second derivative equal to 0 where it's actually a maximum. No, it's actually a minimum. And also, if I just flip that picture upside down, so minus x to the fourth, again, I got a critical point that's also an inflection point, but it's a really flat thing here anyway, and it's a local maximum. So when the second derivative is equal to 0 at a critical point, you might have a max, you might have a min, you might have neither. You just don't know. You got to do some other way of deciding. Okay, but in the event that the second derivative is either positive or negative, then you can say precisely that you have a local minimum or a local maximum, depending on which case you're in. Okay. So there you go, the second derivative test.